Intel Theater, thank you so much for joining us here at Supercomputing 2024 here in Atlanta, Georgia. We're so happy to have you here. We're having presentations throughout the day, every 30 minutes. So we have our next one right now about porting the ExaStar multi-physics applications, FlashX and Thornado on the Aurora Supercomputer. Coming to you from the Argonne National Laboratory, Mathialakan Thavappiragasam. Let's give him a round of applause.
Thank you for the introduction. This is Madhi from Argonne National Laboratory. Actually, I am working with the Leadership Computing Facility under the Performance Engineering team. So here I am presenting the porting effort for the ExaStar FlashX on Aurora Supercomputer. So this is a teamwork. We work with Intel people and Oak Ridge National Laboratory. So as earlier said, this is a teamwork. We are working with Argonne National Laboratory people, and we are working with Intel and also Oak Ridge National Laboratory. So while porting this ExaStar application tool to Aurora, we faced several challenges, but we came overcome these issues by the support of Intel peoples. So for example, Intel COE team, they help to establish the connection between different Intel teams. And the ExaSol performance code design team helped us to identify the roadblocks and solve the issues for the performance porting. And also they worked with their internal system to evaluate our application tool, how it is portable. And the Intel compiler team, they solved the compiler bugs in timely and help to remove the roadblock to overcome these issues and help to port successfully. And the Oak Ridge National Laboratory, they are the domain expert. They help to understand the algorithm very well and also re-engineering the algorithm based on our feedback. This is a kind of evolutionary process. And finally, we achieved the success of porting the ExaStar FlashX to Aurora system. And we are able to scale over the 2K nodes. So this is the linear speed up. And we are also proud about the supporting to compiler development one API. So we gave lots of compiler bugs report. Then they resolve the bugs and improve the one API compiler. So in this talk, I am going to show some specific features of Intel system and also the Aurora and how we utilize those systems to port this ExaStar application. So the FlashX is a multi-physics application tool. So it uses different submodules for complete or accomplish these different subtasks. So we picked Thornado, the submodule Thornado, because it is time-consuming compute-intensive kernel. So compute-intensive modules. It consumes more than 80% of the flops. So we worked on the Thornado application to port Aurora system first, and then we worked with the FlashX. FlashX can be decomposed and distributed over the multiple GPUs, and Thornado can sit on a single GPU as a single MPI rank. So we have to use multiple instances of Thornado underneath of FlashX. Here I saw the theory under the Thornado. I am not going to explain everything, but here this is based on IMAX scheme. So implicit, explicit schemes. So we split as two test cases. So implicit scheme and explicit scheme separately. One is sine wave streaming, and another one is relaxation. In the right side, you can see the how the FlashX is using the sine wave streaming and relaxation apps. So here I saw the traceback of performance enhancement where we started and now where we are. So I saw the two time, total time and IMAX time. IMAX time is exactly the computing time. Total time is it includes from start from end, everything inside the total time. So when we started, it is around 239 and 119 seconds. Now we are in around 10 seconds for both. So we achieved around 23x speed up on total time and IMAX time around 13x speed up. So it is not only for the optimization of code, it also reflects the hardware changes of Intel hardware change and also the compiler versions. I saw the same kind of float for the another app, relaxation. So earlier I saw the sine wave streaming app. Here I saw the relaxation apps. So we did the same kind of optimization on the code level and also hardware changes and also the compiler version changes support us to come to the current position of the performance enhancement. So here I saw the kernel level performance optimization. We use the same technique, general technique kind of loop collapsation and loop decomposition kind of thing. So this is a kind of general technique we use for the kernel level performance optimization. This is a Fortran based code. So we do and OpenMP target offloading. So here I saw the effect of the kernel level optimization kind of benchmarking. So how it helped to improve the performance. So we got nearly 5x performance improvements by tuning the code level optimization kind of loop level optimization for each compute intensive kernels by loop decomposition and loop collapsing kind of. This is kind of general techniques. This is a one important technique we used in the Aurora system, the memory usage-based performance optimization. So there's a technique we can define the memory pool initially. This is a reusable memory pool. So we can configure this memory pool by using the environmental variable libomb target level 0 memory pool. So we have to give the memory type, device or host or shared, and we can define what is the size of memory block and number of memory blocks and maximum size of the pool size. So it is kind of tunable parameter. So we can tune the memory pool size and we can get the optimum value of the number of blocks and memory block size depend on the applications. So the default value of the device memory is 1 and 4. And we did some benchmarking and tuning the memory pool size for our two different applications, sine wave streaming and relaxation. On the right-hand side, you can see the improvement of performance by tuning this memory pool size. So the sine wave streaming, we got around 2x speed up. But for the relaxation, we got nearly 5x speed up. So relaxation app kind of memory bound kernels using the memory bound kernel. So we got nearly 5x speed up for this relaxation app by tuning the memory pool size. This is by compiler level optimization. So by switching from G to AOT, we got some performance improvements. Actually, this switching from G to AOT compiler, we are able to reduce the gap between the actual computing time and total time. I can show the exact effect of this AOT compilation here. By switching the G to AOT compilation, we can reduce the gap between the IMAX time and total time. Okay, so now how we can compare the Intel system, the performance of the Intel system with other system, for example, NVIDIA and AMD system. So Intel PVC has 2 tiles or 2 stacks. So when we are using the 2 tiles, it has some implicit communication between 2 tiles. So when we use the 2 tiles entire GPU for Thornado, we got some performance loss. Then we decided to use a single tile on the PVC for this 1 execution units. So how we can utilize the entire GPU? So we use 2 execution units and and do two tiles, and concurrently we run those two execution unit by using the host threads. And we took the average time and compare with the other GPU system, NVIDIA and AMD. AMD also has two GCDs, but it can be in the software point of view, we can consider as two GPUs for AMD. But Intel is it's kind of it's two tiles, and it is inside the GPU system. And in order to compare with NVIDIA, we choose OpenACC programming model because it gave some little performance improvement than OpenMP. And we wanted to choose the best performance programming model based on the architecture. These are the benchmarking for those sine wave streaming and relaxation apps. So these are just numbers, so it can be changeable in time to time because of the compiler versions and also the performance enhancement. So based on these results for sine wave streaming apps, MI250 is showing the better performance, but for the relaxation app, Intel PVC is showing better performance. So here I saw the another important features of Intel PVC. There's a CCS mode. So for the CCS modes, actually what it is using, so I already said the PVC GPU has two tiles. So inside the tiles, we can further split tiles as a cluster of execution units. So if we set two, then we can split further two stacks or two cluster of EGU units. If we just set four, then we can further split as four cluster per tile. This is kind of same technique we are using NVIDIA using MPS features. So we use MPS features in NVIDIA polarized system and CCS features in Aurora. And for the AMD Frontier, we used we use multi ranks for GCDs. And here the important thing is you can show in the right hand side, when we increase the number of ranks for the 4 and 8, for the 4, the A100 fails to run. You can see that there are some NCs for NC for not capable. We represent for not capable. For the 4 ranks, it fails for relaxation, the large test case. And for the 8 ranks, polarize and also A100, also MI250 fails for the large test case for the relaxation app because of the resource due to limitations. But for the PVC system, it also fails, but we are able to tune the memory pooling size. Because of the memory pooling size tunable, we can able to run the large case of the relaxation app on PVC system. That's the important thing on the PVC system. We are able to define the pool, and we can able to tune the pool size, and then we can manage to run the large test case on the relaxation. Here I am showing the FlashX. This is the main app. So earlier I saw the Thornado. Thornado is the main submodule on the FlashX. We are using underneath the FlashX. So this is the test case we use for the weak scaling. So there's a test configuration, and these are the how we scale for the 2K nodes by increasing the block size to increase the workload size. In the right-hand side, we saw the Aurora system. So Aurora system has 6 GPUs. They are interconnected with XE links. And we measure the form for the benchmarking to compare with the results. So the weak scaling plots in the left-hand side, I saw the Aurora results. So it is showing the linear speed up for the 2K nodes until the 2K nodes. And the right-hand side, we compare the results with the Polaris and Aurora. The Polaris is the NVIDIA-based system. It is using A100. And Aurora is PVC GPU. And Frontier, as you know, that it is using AMD-based system, MI250 GPUs. So here the point one actually the single GPU. So for the single GPU, so Aurora is nearly giving the same performance for the A100, but for the MI250 is giving 2x speed up. For the point 5 is the half node and one is a single node. And for the internode performance, actually for 1 and 2 and for other nodes, it is giving nearly 1.445x speed up for the Aurora, and 1.9x speed up for the Frontier is giving 1.9x speed up. So the same application, we did some strong scaling studies. So strong scaling studies also showing the linear speed up on the Aurora node. So it is we are showing here the 1K nodes until 1K nodes. So in the right hand side, we are comparing with Polaris and also Frontier system. So the Aurora is showing 1.4x speed up. Meanwhile, the Frontier is showing the nearly 1.9x speed up. And here also we use the same technique for the FlashX, the CCS mode. So instead of going to internode scaling, we did some intra-depth scaling. So inside the GPU, we can split the GPU further, as already the PVC GPU has 2 tiles. When we setting the CCS mode, we can further split the tiles as CCS modes. So for the intra-depth, in the y-axis, you can show the intra-depth using the 2 CCS mode and 4 CCS mode. We can speed up by 1.7x and 2.2 or 2.3x speed up. And internode scaling, also we can increase the speed up. So by using combination of intra-depth and inter-breadth scaling, we can get good performance, like from 1 to 14x speed up by using 8 nodes and 4 CCS mode. So this is another features in Aurora system. We can further go deeper in the GPU by using the CCS modes. This is kind of same technique using in NVIDIA system for multi-process system, MPS. This is a summary of our work. So FlashX, we successfully scaled over 2K nodes in the Aurora system. And also we identified 2 important features of Intel system. One is the memory pooling configuration and other one is CCS modes. We can go intra-depth within the GPU by scaling intra-depth. So by using intra-depth and inter-node, we can go good performance scaling with the resource utilization, high resource utilization and occupancy. And right now we are working on the actual science problem in 3D case, CCN, CCSN, and also using the another features of Aurora system, DIOS file system. It supports for parallel file system and huge memory for the handling file system. So for 3D case, we need we need to handle the huge file system. That's why we are working on the DIOS file system. And also we are preparing benchmarking for the feature system by using this FlashX and Thornado app. Yeah, that's my final slide and some acknowledgements. So this is the project we work with Oak Ridge and Argonne National Laboratory together.